Yeah, my wife was talking about the storm in 95. She's from the Bay Area. She's got a friend up there, and apparently they're out of power for 2 days from that storm. And this storm's not quite that scale, but it's there, close to it. So Dijkstra's single point, shortest path algorithm. So from a given starting point, the objective is to find the shortest path in a weighted graph to all other points in that graph. There is a restriction that the weights of the edges are all non-negative. This algorithm falls into the greedy set of algorithms. The algorithm is one that takes the best option when it gets to making a decision. All right, so from the starting vertex, look at each neighbor we have not established shortest path to. And look at the costs of building a path to each of those neighbors. Link to the Google Doc, yes. There you go. This builds a set of possible paths, or potential paths that we can build upon. From amongst the available paths, we'll be greedy and choose the shortest path that we can build and build to that vertex and mark that vertex as the shortest path. And then we'll repeat until we know the shortest path. We know the shortest path to each vertex. Ooh, can't see my changes. Okay. Seems my internet might also be glitching myself. I need access. Okay. It's always fun to need access to my your own resource. Good old refresh. Let's see what can happen there. That's fine. Reload. Fortunately, we hadn't gotten very far with our graph. All right. So we'll drop a few vertices on the graph here, then we'll add some edges between them. And then build some paths. All right. Okay. All right, let's add away from A to B for 2. A to F for 9. A to G for 4. Let's make it 3. B to F can be 5. G to F will be 2. B to E will be 1. F to E for 3. E to C for 6. C to D for 2 again, and E to D for 3. All right, so what we're going to do is have a table that's going to represent all these find data points 2, 4, 6, 7. All right. All right, so the first column will just be all of our vertices. We'll do alphabetical order just because. All right, the distance to that vertex from our starting vertex, which we'll just arbitrarily have as A to start. How we're getting to that vertex will be the next column, so we'll have that source vertex. And whether or not we know if that is the shortest path to that vertex or not. So starting from vertex A, our initial state, our distance to A will be 0 because that's where we're starting. And we know that to be the shortest distance. So our initial table state will have one record filled in, everything else just default values, right? Unknown, null, false, whatever it is that we're using in our object to track. All right, so what we want to do is go ahead and get A's neighbors. Neighbors and update the table. Potential paths. We can build from there. All right. Go ahead and annotate. All right, so we have orange paths will just represent potential paths that we can build. So we can go from A to B, A to F, and A to G. So we'll just update the table accordingly. All right, so we can get to B from A, and it would cost us 2. And we'll just fill the whole row right here. While we're here, we can get to F from A for a cost of 9, and we can get to G from A for a cost of 3. We don't know which of these is the shortest path yet. All right, so now that we've finished processing the data that A can give us, we need to make a choice. Choice of which path to build. We can build to B for 2, F for 9, or G for 3. Being greedy, we'll take shortest option to B. We'll open the test up at 8:30 or thereabouts. So what we're going to go ahead and do is mark B as known. So we set B is true. We'll go ahead and mark it as green. That we have built a path. So we now know the shortest path from A to B is going to be 2. All right, so the rationale for the greed here, since we're taking the shortest path here, alternate paths, like we could go from A to F to B, adding in the total of these paths, of the edges on that path, to give us the total path length. But mathematically, that's going to have to be larger because this first branch is going to be greater than our first option because we selected 2 as opposed to 9 because 2 is less than 9. Same thing with other branches that we might take, or other routes we might take, rather, to try to get to B. So that's the rationale behind the greediness, which is why the weights have to be non-negative. We don't have a discount, right? They're not paying us to go from F to B at a cost of like -10, something like that, because then the algorithm would fall down because 9 plus -10 would then be less than 2. That's the restriction about the weights. Okay, I have a question. Isn't F to G to A count? F to G to A, F to G to A. That's a route we could get to, and we will once we're finished processing the edges. All right, so someone's already jumping ahead and seen that AGF is a cost of 5, which is the reason why I made A to F such a large number, because we're going to find alternate routes. In fact, we're going to find the alternate route here from B to F at a cost of 7 first, and then later we'll find out that we'll improve upon that path later by replacing the ABF path with an AGF path. All right, so now we're at B, and we'll go ahead and process its edges, right? Because that tells us who the neighbors are. All right, so let's get our orange lines in here, right? So we have 2 edges that are not yet processed, right? So the A to B is already processed edge. It's not going to give us information we didn't already have. So now we can build a path from B to E after getting there from A, and we can also build a path from B to F after getting there from A. So our E entry, go ahead and say we can get to E from B for a cost of 1 plus 2, right? So the 1 is the transition cost from B to E, plus it costs us 2 to get to B in the first place. Don't know if that's the best path yet or not. And then we have B to F, which would cost us 5 plus 2. Since 5 plus 2 is better than our original 9, we're going to replace that path in the table. So we're going to go ahead and basically raise. Yeah, let's do a stamp. Say this path is no longer considered So we found a better way to get to F than the direct route, right? 5 freeway at traffic time versus side streets type situation. All right, so that's giving us all our information from B. So now that we have finished the edges from B, we'll look at what paths can build. All right, so we have E for 3, F for 7, and G for 3. All right, so in this situation, that's about right. Try to fix something that's not wrong. Okay, in this situation, we have 2 equivalent options. So we'll default to another computer. We deal with this and keep the first smallest value, as we'll only replace with smaller when finding them in. So we'll take the path from B to E. All right, so when we go to B to E, we'll flag that as the shortest path. And then we'll go ahead and repeat the process. Just go ahead and see what edges E can tell us about. And update our table accordingly. All right, so we have 3 edges coming off of E. We can get to C. Get to C from E for a cost of 6 plus however much it costs us to get to E, right? So that information is here in the table. Get to E is 3. So the 6 plus the cost to get there was bringing us to a total of 9. Since that's better than no information, we'll leave that 9 in there. E to D, same situation. Getting there from E at a cost of 3 plus 3. And then E to F is a 6. And that's also an improvement. So we're going to go ahead and throw away the old information and say that our 3 plus 3 is a shorter than our 2-hop path. And well, that didn't work. What was the shortcut? Alt Shift 5. Okay. Let's see if I can remember that one. All right, so all 3 edges that we found building our path to E have been processed. So we can just be greedy again. And we'll take the 3 we didn't take last time. And build a path to G. So let's clean up the table, the math, just have our fixed values. Oops. Just the 6 there. There's the E, and we're building our path to G, so we'll go ahead and flag that as true. Then G can tell us about the path to F. Right, so it's gonna be one edge. One edge from this point. Process G edge. All right, so we can get to F for cost of 5. by going there through G instead of E. Let's hit the right shortcut keys and we'll get there sooner or later. Get there sooner or later, perhaps. All right. Only one more edge left yet to process, but we do need to keep on processing and see we have eliminated. Let's get my stamp. Did eliminate those paths when we said we wanted to build from 3 plus 2 to F. And keep processing. So we have 1, 2, 3 vertices that we're still building a path to. I do have to draw in my arrows here. All right, we know how to get to G. All right, 1, 2, 3, 4. 1, 2, 3, 4 vertices that we have paths that we know are the shortest possible based off of the processing that we've done so far. All right, so our options. C for 9, D for 6, and F for 5. All right, so we will take our shortest option as we have been. Keep the greed machine rolling. And then process from F, which we will see is no new information at this point because building our path to F gets us to a vertex that we already have all the edges processed. All right, so no other updates. As building our path to F brings no new edges or no better edges into the equation. Down to 2 choices. All right, 2 choices left. C for 9 and D for 6. All right, so everyone good on which of these 2 paths we're going to build from? Which we'll build to next. All right, so 1 vote for D, 0 votes. So we'll go ahead and build our path D. We're going to get to D from E. Let's go ahead and draw in connection. And we do have 1 edge to process here. Presently, to get to C, table tells us we can get to C for a cost of 9 from E. Alternatively, it gets cost 6 to get to D, and we have this edge for 2 as an alternate route. And that gives us a total of 8. All right, so that 2 plus 6 is going to be an improvement over the existing paths instead of going from E, we will go ahead and instead go from D. All right, last option. Just need to mark it as true. And we will have completed the process. Right, that is true. Update our drawing. We have all the paths in here. So the same thing they have in the drawing is the same information that we have in our table. I want to know how to get to G. All right, we get to G from A. All right, direct path. I know how to get to F. F says I go to G, which then takes us to A. And there's the path there. E says we're going to go to B. B says we're going to go to A. All right, so all the information is in the table. Not only the costs that it will take to get from a vertex to our starting vertex, but also the actual path to get there. Let's grab this as well. It's the same information in both places. Just one's visual, one is data. And it looks like I did miss a stamp here on 6, but all right, let's fix that. We're not too far along. Kill that one. And try to get back in. Give me the mouse. Thank you. Right. So if A is our house or school or work, wherever we're going, we want to know it's the shortest way to get to all these various points that I might be going to. We have it all laid out. And we know how to get there. Questions at the moment? Let's do another example. Keep this one small. Basically similar to, just do it small. All right. All right. I presume there are no questions at the moment. Source column is one selection. The source column tells us who our predecessor was to get to where we are in a particular path. Right, so our source vertex, right, to get to B, we go from A. Yes, it can possible paths. And then as we find better paths, we're also greedy in that step and we throw away lesser information or worse information. Yeah, so until we flag vertex as known to be the source path, the source vertex is in flux. Okay, so let's go ahead and get our table here. And a few, too many rows. Delete, delete, delete. There we are. Okay, so let's start at E this time. We'll start at C. C is our starting vertex. So go ahead and mark that as 0. We know that's the shortest possible distance to C because that's where we are. Doesn't cost anything to stay where you are. There's no transition cost. So we'll have two edges. All right, let's draw on here. All right, B and C and D and C as our paths. I guess we need some weights. Let's get some weights in here. This is neither, the question is asking if this is depth or a breadth first traversal. This is not a traversal. This is a shortest path building. There is some similarity. But completely unrelated for what we're doing. Right, with the breadth first and depth first search, we're looking to find the vertex, often ourselves, to see if there's a cycle. Here, we're trying to build a path from a single point to all other vertices, which is something of a search, but except that we're searching for everyone, and we're tracking our costs to find out who is the shortest amongst all those options. All right, so just going to toss in some weights in here. On our edges, and then we can start running through the algorithm. Yeah, one's good enough. All right. Okay, so we could get to B from C. We don't know that's the shortest path yet, and it would cost us 2 to get there. All right, so we got the direct hop from C to B for 2. And then we also have the direct hop from C to D for 1. All right, so we'll be greedy and choose our C to D path. Mark that as true. And then go ahead and see what we can build from there. Okay, change my mind. I do need this on the side. All right. Try to keep my colors consistent here. And we chose to go from C to D. Right, that will give us 2 more edges to process. All right, so this time we're looking at the total cost to get from C to D, right? And it costs us 1 to get to D plus 6 to get to B for 7. And since 7 is not an improvement over 2, that edge doesn't live long. We consider it, and then we immediately discard the information. And we get over here to our DE edge. All right, so we can get to E from D, right, for a total cost of 4. All the edges from D have been processed. And we have 2 choices, B for 2 and E for 4. So we'll go ahead and mark B. Go look at what edges it can tell us about. Right, draw that we're taking the path. All right, so the path is set from C to B. Now know how to get 2, 3 vertices inclusive of our starting vertex. 2 edges to consider. All right, B to A for an additional 1. So we can get to B from B to A for an additional 1. It cost us 2 to get to B. So that'll be 3 to get to A. B to E is 3. Costs us 2 to get to B, so that'll be a total cost of 5 to get to E. That 5 is not an improvement. With the existing information we have in the table, so we will not replace it. And we've finished processing the edges coming out of B.
Sorry, Professor, could you repeat that last part starting at B?
All right, so we decided to build a path from C. So we just built this path from C to B. Now we're considering the information that B can tell us that we didn't already know. The path from C to B to A for 3. And the path from C to B to E for 5. Right, so the 3 was an improvement, or because there was no information there previously, but the path to E from C to B, E costs 5. However, the path to E by C to D to E, it costs 4. And since that's not an improvement for our new path, we do not update the information in our table. All right, so at most, each row in the table tracks a possible path, and that possible path being the best path amongst paths that we have seen so far. A new path can be built to a vertex that is an improvement upon the path that we've already found. Then we'll replace it. If it's not an improvement, then we'll go ahead and discard the new information. It doesn't make it into our table. Okay, so we have choices. We can go to A for 3 and we can go to E for. So we'll go ahead and take the shorter of the two, being greedy. Go to A. And then see if it has any edges. We've got the 1. Let's go ahead and take a look and see if this new path is going to be an improvement. All right, so it's another 5 path. 2 plus 1 plus 2. We could get there the other long way around for a total cost of 5. Current information we have there for E is 4, so it's not an improvement. So we'll go ahead and discard that information. And then the last thing we need to do is just mark our last vertex as the best path that we could determine. And we got there from D. Right, so our drawing here and our table here are the same thing. Right, so the green arrows represent the shortest paths. Right, to get to B, straight up from C. To get to A, C, B, A. To get to D, straight up from C. To get to E, C, D. Okay, so same thing, except we reread it in reverse. So if I want to know how to get to E, I look at its entry in the source vertex. Okay, we got there from D. Then I jump over to D's entry to see how we got to D, and it says we got there from C. And C is our starting vertex. So there's no further back. We need to look in the table. Let's do this one more time. We'll do a cycle. Right, and we can see the paths growing. Okay. Let me go grab that. Oh, I killed the Google Sheets again. Somebody's got to do it, I guess. And out from the ashes, something new can be born. All right. Yeah, let's just keep it. Yeah, we'll take it all. So the question is, do we use Boolean variables that indicate we're done or count? There will be Booleans. You'll have a true or false record tracking. If you have built the path to a given vertex, and once you knock them all to true, you're done. There's all kinds of optimizations that we can do to how we maintain this table, right? So the table is abstract. It's not defining how we need to represent the information, just information that it needs to support. Right, so we can maintain separate lists, right? We can maintain a separate list of unknown vertices that's maintained in a sorted order. So we could just do a sorted array, we could do a sorted linked list, we could do a min heap, because we're gonna repeatedly ask the question, who's closest, or who's the shortest path that we can build? And there's only ever going to be the one value, and that could be the top of the heap or the front of our sorted list. So it's just a matter of how we want to maintain that data. Okay, let's build my cycle up here a little bit. All right. It seems like a big enough cycle. Do some label fixing here and add in a few weights. Yeah, a min heap would be useful for some of our data tracking. Right, as you'll find with a lot of data structures, or excuse me, a lot of algorithms for database operations where you have sets of data and complexity in the data, a lot of the data structures that we talked about, several can be used to solve the problem. It's just a matter of which one is better suited for adding and tracking and maintaining that data. Right? Just using arrays for everything would be the simple approach. Right? If we just had an array and just a record type that has the 3 values, and we just keep iterating from the first entry to the last entry, looking at it, see who's false, and then just finding the minimum, right? So linear, 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 but it's not efficient. If you have a 100-point graph and there's 4 options, iterating through 100 records to make a decision amongst 4 options is a non-ideal solution, even though it of course will work. All right, let's go ahead and 1 second. All right, more edges, more weights on our edges, and we'll find out what the path is going to be from A to everyone else here. So let's clear out my annotations, get a new screenshot, and see the ways to go. All right, so that's kind of annoying how it brings up all the other windows. All right. So our table will start with A being populated and everyone else waiting to be determined. Let's see. We got G. All right. So the distance to A is 0. It is our source vertex. There's no entry there, and we know that's the shortest path. All right, so like before, 2 options. This time from A, we can start building our path to B, right? So since this is a cycle graph, right, each path is going to keep building, and as one path starts to get too long, we're going to switch over to the other path, and as that path starts, we can switch back and forth depending on what our weights are and how far down we've gone. So to B from A for 1, don't know if that's the shortest path yet, and E for 2 from A. All right, 2 choices. Be greedy and take the path to A. Let's see how many times we copy our table here. All right, path from A to B is chosen. B is just going to give us the one edge, as is always going to be the case in the cycle graph, just one new edge to give us information. Right, so what's the distance to C going to be? What entry should I put in this cell? 1, 2, 3. We have 3s. All right, 3. Total cost to get from A to C is 1 + 2 for 3. Don't know that's the best path yet, but we will find out that it is later. All right, 2 choices, a 2 or a 3, so we'll toggle back. Build a path to E. Mark that as true. And find one edge. Get to G for 5. G for 5 via E. Don't know that's the best path yet. And we'll switch on over back to the other side. I'm going to go to C. Oops. And see what new information we can find from there. One edge as before. Costs us 7 to get to D. From C, we don't know that's the shortest path yet. And right, 2 choices. Right, only 2 roads that we're building here, so we'll take the 5 to G. Mark that as true. Overreaching on my highlighting. And that'll tell us about another edge. And we keep working our way through the edges, right? You'll notice that in all our examples, every single edge will get processed. All right, so the question is, how can you be sure the path is the shortest without examining all the weights in the cycle? Right, that's the greedy logic that we did earlier, right? Because there's multiple paths, right? So, right, from A, we can go all the way around the circle to B instead of going our straight hop. The only way that the total cost path length from A, G, F, D, C to B is going to be less than whatever the value is from A to B is if this first edge is lower, right? So let's say A to B is 20. Right, we can pretend that that is a 20 as I draw in straight lines. Right, so we don't take it initially because we have a choice between 2 and 20, so we build down. We have a choice between 5 and 20, so we take the 5. We have a choice, we have 6 and 20, so we take the 6, 8 and 20, 12 and 20, 14 and 20. So we ultimately do see that, okay, whatever the congestion cause of this link is, it is actually faster to go all the way around. But if that number were something smaller, let's see, what kind of That's why it was being weird. Let's say it's, okay, not 12. Let's make this a 10. All right, so if we build 2, 5, 6, 8, and we get to this point, we're comparing 8 to 10. So adding in 4 to go this way is going to be more costly than it is to go straight across. All right, so it's just that the transitive nature of the math as we add things up, because as a path gets longer, the costlier that path gets, and the less viable of an option it becomes versus the other paths that we've identified that may have fewer hops and less weight. Okay, let's get my undos. Try to undo. All right. Where's the eraser? I killed my snip and stretch. All right. Well, okay, let's get a new drawing. All right, so we only mark a path as known once. We mathematically determined that we will be unable to find a shorter path. Okay, computer, you can do it. What is eating all my, 1 second, just pop my task manager up here to see what is freezing me. Hopefully you can still hear me. All right. Well, CPU's 11, memory's 43%. Just Windows was having a little bit of a panic attack. Okay, let's try to get a screen grab again. Try to get the snippet to open up. Oh boy.
Seems like we can hear you, but your screen is frozen now.
Yeah, my programs aren't working with me at the moment. It's definitely okay. Can you see the graph screen grab again?
No, you're still attempting to take a screen grab right now.
Nice. So it's probably Zoom that crashed on me a little bit here. All right, so yeah, it's been an hour. Let's go ahead and we'll take a 5-minute break. And I'm just going to reboot my computer and I'll come on back. Okay. Yeah, so we'll take a 5-minute break and we'll be back at 5 after. As I try to stop the share. There it goes. All right. Party can get started again. Let's see. Back to our cycle. Let's see where we were. Getting there, getting there. It's always fun to reboot and lose all the state that you had. So let's see where we are in our graph. Draw all of our, it's the right color. All right, so we had the possible path from A to B, E, all the way up to G is true, if not yet known. B to C is in there. That's also known. We do know about DF. Okay. Let's get our paths. All right, so at this point, we've built a path to G for 5. We've built a path to C for 3. And then the predecessors B and E that are along those paths. So again, we're at our choice. Let's see, missing information. So see, we just built our way to G. So new information is going to F. An additional 1 from G, so we have 6. From G, we don't know if that's the shortest path yet or not. So we'll flag that as false. Now we have 2 choices, 6 versus 7. 6 wins out, so the path we just found is shorter. And we can find out about our last edge to D from F. Right? That would be a total cost of 6 plus 2 as an alternate route to get to D, which is presently at 7. And so since that is not an improvement, we will discard that information. And we will choose the way to D to be from C. And we've established our shortest paths. So if we did have a scenario like we mentioned earlier, where we have a big, heavy costed path here, since it is a cycle, there's guaranteed at least 2 paths from one vertex to any other vertex. If the one way doesn't get us where we want to be or how we want to get there, then there is that one alternate route. So it's all about the cycles. The more cycles there are, that means the more alternate routes there are going to be. Right, so you have more of a tree graph here, and if we get rid of this edge, right, our options are basically nothing. We build the path. There's one way to get to E. There's one way to get to everywhere else. So the table is going to be very, very limited. So there are no cycles in this graph. So there aren't any alternate routes to consider. So it's just the one and only way to any other vertex. So certainly not a good network. you'll typically see Dijkstra's algorithm being used to maintain router tables. So when a packet comes in, we know the way to go. No, the cycle, the first choice is just what the first choice happens to be. We might be building, we'll just be building, we could be building in one way for a long way if the second option was quite heavy before our total cost gets to the point where it is outweighed by the other one. But eventually we'll determine what the shortest path is everywhere, and we'll get to where we're trying to go. Okay, let's rename this one to single point. Grab our Floyd Warshall and toss that into a new doc. Dijkstra is taking up plenty of pages in that first one. 7, okay. Okay. I got real big. All right, tossing the link into the chat. Yeah, the reboot wasn't going so well. I had to forcibly power because it just kept shutting down. So I probably broke an update at some point. But anyways, sooner or later you always have to reformat and start over because too many things collect. Okay, so with the previous algorithm, we want to know the shortest path from any vertex to any other vertex or all other vertices. Just rerun the algorithm for each vertex. And that's something along the lines of V times V plus E repeated E times. So there's a fair bit of us there. So alternatively, we need to know the path is just us. We have the Floyd Warshall algorithm. Just 3 nested loops and do some comparing of alternate paths. I'm on Windows 10. So had to endure Windows bugs yet. I've heard there are quite a few, plus they've made a lot of UX changes that I'm not interested in. Okay, let's get a drawing in here. Smallest. This particular algorithm is V cubed. We don't want to go too crazy. Remember, vertices will be here all night on just one example. All right, let's go. And start with this 5-point graph, and we'll add some weights in here. Let's see, try and do some thinking ahead here so we can get some good updates. That should be enough. It's not too horribly connected. So A to B is 3. A to D is 5. B to E is 2. D to E will be 6. C to D can be 1. And I have B to C as 5. All right. Let's go ahead and grab pseudocode. All right, so I have for loop. K from 1 to the number of vertices. A. Get the font bigger here. Let's see. That looks good. All right, I the same thing from 1 to all the vertices. And same again with J. All right, so we'll be using a matrix here to represent the graph because we want to do a bunch of indexing. So we're going to look at the direct path from a vertex to a vertex versus going to a jump point. All right, so for example, we're trying to get from A to C, which we can't do. Alternatively, we can jump from A to B and then B to C for a cost of 8. And that's the type of information that we'll be looking at. So that alternate path shows to be shorter, we'll just go ahead and update the matrix with that alternate path. So let's get our table in here. Label out our vertices. All right, got to build our matrix. As usual, it's a simple graph, simple weighted graphs, which as edges are defined, add the corresponding entries to the table for their weights. And I got it. Misfire there. Got A in the wrong column, so let's fix that. All right, BC for 5, BC for 5, and BE for 2. C goes to D for 1. And D goes E for 6. All right, so what we're going to be doing first let's see. Where's my fill? It's fine. First, we're going to use A. So the algorithm says K equals 1. So they're using 1-based indexing in the pseudocode here. So column 1, row 1, column 1, row 1, column 1, row 1 type thing. Let's see, highlighting work. It's fine. It's highlighted. So A is our reference vertex on the first pass. Color that as well. And we're going to do some comparison. So we can ignore the entries in row A, column A, right? Because alternative, instead of A going to A for 0, so we're going to do is look at every single element in the table, compare that value to corresponding. So when we get to this 5, look at the sum. I guess actually I need to update my table here to be dashes indicate no edge, so we don't confuse the zeros in our math. Because there's no connectivity there. All right, so to get from A to A, we could have A go to B, which brings us to the B record, and then B can go back to A for 3. So we can go and jump from A to B and then back for a cost of 6. Since there's no information presently in there, and go ahead and update it. In fact, let me do that update over here. 6. Get the dashes back into position. Trying not to corrupt the process. Okay. All right, so we updated with 6 because that's an improvement over the previous information, right? So we can just skip in general this type of stuff because we'll actually get to that one when we are processing B, and take this 3, take this 3 and this 3, add it together and give us that 6. All right, so skip, because the first row, when K is 1, I is 1, J is 1, we're comparing itself to itself plus itself. So assuming all non-negative weights, mathematically, it's impossible for U to be bigger than 2 of U. And a lot of the tests in this algorithm are that kind of math. So the first place where we actually have meaningful math would be to B. And so instead of not knowing how to get there, A can go to B for 3, and then B can go to A for 3, and then that gives us our 6. We'll do the same thing over here. We'll look to see presently it costs 5 for B to get to C, right? That's what the matrix tells us. Alternatively, it could go to C for an unknown quantity, and then we can add in an additional 3. Since there's an unknown quantity there, infinity, as it were, cannot improve this 5. All right. We're here at D, we have no information, so we'll get some improvement, right? So B cannot get to D. B has no connectivity to D here. Alternatively, A can go to B for 3, and then A can go to D for 5, and then 8 is an improvement over no connection. Same test again, comparing 2 versus infinity and 3. So the 2 is already better, so we leave it alone. Right, same things again. We're looking at A and seeing if we get improvements. C has no connectivity to A at all, so this entire row will find no improvement. This lack of connection, though, right? A gets to B for 3, D gets to A for 5. It's the reverse direction. So we can go from D to A and from A to B for a total cost of 5 and improve our weight there. Here we have a D to D. D can go to A for 5 and then back for 5 as an improvement, and then E column, no information. So this 6 holds out. And then the last row again, no improvement can be had because there's no connectivity, no alternate route that we've built so far. At this point in time using A. Right, so we just finished the nested pair of inner loops for k equals 1. K bumps up to 2, and we'll do the whole thing again. So now we're going to be using B as our reference point to see if we can jump to B and then elsewhere to see if we can get improvements. Right, so it gives us our 3 plus 3. And we can replace no information for how A can get back to itself. Right, so what's the closest store I can go to A so I can make breakfast? Right, so you need to, you're starting at A, and then you're leaving A, getting to the store, and then you're coming back. So you're basically finding what's your callback that you can get to is a round trip communication. All right, so record C, no information versus 3, 5, and 8's an improvement. A is presently 5, 3 plus 8's not an improvement, so we'll leave it alone. Connectivity between A and E, so 3 plus 2 is an improvement. B is our present reference points. We can go ahead and just skip the row. So go and jump down to C. 3 plus 5 is better than nothing. 5 plus 5 is better than nothing. Right, A plus 5 is not better than 1. And 2 plus 5 is going to be better than nothing. So we'll set a 7 there. Down over here, D going to A. 11's not an improvement. 13's not an improvement. 16's not an improvement. And 10's not an improvement over 6. Last for this path, right? 5's an improvement over no information. Reference point, nothing to test there. 7 versus no information. 10 versus 6, leave it alone. And then we have our loop back of 4. All right, so we finished using B as a reference point that time around. Copy my graph in here. Update. Let's see, there we go. And we keep on rolling, same idea, just moving who our reference vertex is down the line. This time we're going to use C and check our hops. Iterate over every index in the array, testing the sum of the highlighted entries that match up, right? A goes to that 8, A goes to that 8, 16 is not an improvement over 6, we leave it alone. That 5 plus that 8 is not an improvement over 3. Right, same story, all the values in this row are smaller than our jump to C, so we're not going to find any improvements. Our row B, we have 5, so anyone that's less than 5 we can ignore. 6, same idea, because 1 would be the greatest. This 8 though, comparing 8 versus 5 plus 1, we can get an improvement here. Drop that to 6, and no improvement on 2. All right, 9 versus 5, mirror. 8 goes to 6. I've found a shorter loop back. Previously we had 5 plus 5, now we got 1 plus 1. And 8's not an improvement. Rolling through, that's a 7, so all done. At that point, I just realized I was updating the wrong table. Let me, okay, All right, who do we have here? We had the 6, the 6, the 2. And do we have anyone else? I believe that was it. Two more vertices to consider or suffer through, depending on how you want to look at it. Next, and then after we're done with processing D, we can get to E. All right. Okay. So now we have a 5 to look at. 10, 6, 11 versus 3, and we got an improvement for A to C. All right, so let's go back. Right, A to C does not exist. Right, there's no direct path. So we're looking at D as an alternative. A to D for 5, D to C for 1 gives us a total of 6. So we can go ahead and improve what it takes to get to C. And previously we had a path of 8 by going to A, B, C, and we decided to go ahead and toss that information and replace it with a 6. All right, and we'll do the same thing for all our data points. All right, so this one's a 6, so only the records less than 6 can improve. 1 here, so lots of room for improvement. 5 plus 1 gives us improvement. 6 plus 1 is not. 1 plus 1, loop back in the other direction. And a 7, so that'll stay the same. Reference row, so we'll skip D. And then lastly, we have row for 6, and 7's our closest value, so we're done. Further we go, fewer improvement likely to find because we've already been doing some improvement, but depends on how disconnected things are. The more disconnected things are, the more paths we can build out as we go along. All right. So like before, so we have a 5 in a reference, looking at all the values, we're not going to improve. 2, we have potential. Do some math, right? 3 versus 7, no good. Here we have an improvement. So we got better loop back for 4. 12 and 8, no good. 7, no improvement. 6, no improvement. And we're done. And here we have our final answer. Shortest possible path to get from A to A is going to be 6 with our loop back to B, right? We don't know that that's the path to get to A, but we do know it only costs us 6 to make a round trip. We're starting at A. A to B will be 3, A to C will be 6, right? Which ends up being this ADC. 5 to D, which is our direct hop, and E, and it being 5, right? So there's 2 ways that we might have gotten here that are direct without extra hops. Right, A, B, E, and A, D. There was an alternative path. If these weights were smaller, it's possible we could have gone the long road, A, B, C, D, E, to get to this point. If A to B were sufficiently high enough and B to E were also sufficiently, or I guess the key point would be B to E and A to D were heavy. Right, let's take this and do a quick comparison with alternate numbers. All right, so if we go ahead and make that a 15, that'll probably be big enough. Make that a 1. My 15 got all okay. Just edit the graph, thank you. All right. All right, so we would have been building paths. When B became the reference point, I would have identified that we could get from A to E for 24. So 24 would be sitting in the table at a point in time. A to D would have been sitting there for 15, so we wouldn't have been using that road for much of anything. We would have built the path from A to C for 8. Then we would be looking to see where we can jump to from C. And so we already have the 8 path. So we've added in there 1 from 9. Oh, my numbers aren't quite big enough. I need to shrink. Getting all the way to 15. So let's make that a 4. All right, so A to B for 3, plus C for 8, plus D for 9. So we'll eventually find this 13 once D became the reference point and replace the 24. I guess the numbers were good before the 24 that we had when the actual path being this road here, and this A to D path actually would have been thrown away because it was replaced with our 9 path. All right, so I'll leave this one here as an exercise. The matrix is symmetric because it's a symbol graph, a weighted symbol graph. So with a symbol graph, the edges both ways. So you're correct, your matrix should have been symmetric across the diagonal, and the final answer will also be symmetric across the diagonal because it's still just a simple graph. I suppose you could do mirror updates, pseudocode, and do a mirror update, right? You could say Dij is that, and you could do Dji is also the same thing because it's symmetric. So you could tweak the algorithm. Might be a slight improvement there, but other than that, I'm not aware of anything off the top of my head. All right, so our big one. It's easy. All right, V times V times V. V cubed. All right, triple nested loop, and the body of the loop is just a constant statement. Let's go straight from functional notation to notation without any code complexity to really worry about. Okay, let's see where we are. So we have this tonight. Hash table due date is wrong. Let's fix that over here. Let's make that next week. Should probably get to hashing next week, but we'll see. Okay. Graph looked to last week, so let's do C# as well, and then we can translate to C++ if we want to. Let's see. All right, I guess that's gonna zoom. All right. Any questions about those shortest path algorithms before we switch back, talk about the lab code? In fact, actually, I think I already did a C#. Buggy, didn't I, before? So I guess we'll go ahead and do C++. Now let's keep it all separate. I don't have to keep it all separate. So what we have here, right? So we have our weighted graphs. So the node is going to be representing a label, or rather a vertex. We'll have our label in there, and we'll have a weight, costs to get there. So taking an abstract of our adjacency list in code is a little bit different than our matrix. Our matrix is pretty easy because an edge being by a pair of vertices is easy to see because it's just an element inside the matrix. But with your adjacency list, right, the weight applies to the edge, but we don't have quote unquote an edge anywhere in the code. The way we're going to do this, right, is by the fact that I'm pointing to a node. So that will have the weight in the node to track that. All right, so list node just going to have the head of the list. And second, let's see. All right, so the list node has the head node, and we'll just add to the head node as we get in there. All right, so I'm going to keep let's see, string label and weight. I'm going to keep the list node class simple because I don't want to spend time adding sort of lists as before. All right, but let's do two cases: if the head, and we'll do a tail. Whatever. It's null. Equals tail equals node. Let's get a constructor in here. And equals W. Do our build out. Otherwise, I'm just going to have tail next equals our new node. So keep my method quite lazy. Lazy version should be doing in order. Our class. This has its array of linked lists. So we're going to have our list star our lists. And we'll do constructor. Let's make these private. At least do some monochrome of encapsulation here. And size. And what is going on with my cursor? That's weird. Really am certain. All right. Ooh. Find out what bugs I have in my code in a little bit. How many vertices? And we'll get our graph. Ooh, freaking type. Typing apparently is a challenge tonight. And next step, of course, is the loop like we had before. To capture and build the labels, all that fun stuff. All right, so let's just add a void set. All right, so the fact that our node has a label in it, go ahead and have list just the very first node in the list be where we're storing our labels. Works either way. Want to do that? Let's see, 'cause I'm missing right here, aren't I? Okay. So for however many there are, my listener size X plus. Vertex label. Get the input from the data from the user, drop that in. I guess we don't really need our own local library here. Skip that. Go straight to our lists. Sub I. And set the label. And print graph. Again, we have an array, so we have a loop. And we'll just do a dump out. Yeah, funny seeing we got out. See out and we'll spit out the label and line. And let's see what we got here. See if we can make a successful 2 vertex graph or not. Let's see what I goofed up here. Right, syntax. Semicolon. Oh, lost a curly brace along the way. All right, let's see. Where am I getting my strings? Always the thing with C++. Let's see. List star site. Got my arrows in the wrong direction. That's not gonna. And of course, copy paste means the bug has replicated itself. Right, that's gonna be head. Label, did I make that available? Yes, I did, so we can see that. And copy paste the bug just means the bug exists twice. We run out of bugs yet? So many new bugs. Can't convert from, oh, got my start. 2 vertices. I guess I should call the print and the set labels if I actually want that code to be called. Would be helpful. And print the graph. And let's see what we have here. 2 vertices. And code's broken. It's always fun to have bugs. All right, switch to actual IDE and we'll find out what I've broken. Questions at the code at the moment before I figure out my bugs. Let's see. All right, how are we doing the font size? We're still good? My reboot build things or not. Sound still Monday, font size is good. All right. Let's see what we broke. 2 vertices, create a graph, change looking, size. My size is all kinds of wrong. What? No, there it just wasn't showing to me. Okay, it's 2. Get my A, see what my bug is. Access violation. All right, let's try that again. Sound is coming in and out. Always fun. X string. Didn't like the string. Well, let's in scope. Try that again. Lists have head. Oh, I should be calling add. I create. There's my problem. List node, create a list node, but I never actually add. Okay, so let's see. How do I want to do this? Yes, we'll keep the labels in the list class. All right. Yeah, if my sound cuts out on you and need me to repeat something, please let me know. I'll repeat it again. All right, so there's 2 ways we could build a list. I just call add and have the head and tail become the label. For the node, which just set some sort of -1 value for the weight because there's no weight yet because there's no connectivity. We just have vertex A and vertex B where the A label is inside list node. Alternatively, you keep the labels here in the graph as a separate entity. It's kind of a 6 of 1 or 6 of 1, half a dozen the other type situation here. Doing that is probably a little bit better. Do it this way. Stay in the graph class itself instead of going deep into the list. But there's always more than one way to slice the pie. And hopefully things work better now. I didn't explode. It's always an improvement, not exploding. And it's always super helpful to have a IDE so you can see what's going on inside the machine to figure out where the rust is, where the nut fell down into the manifold and all of a sudden is beating up the engine. And that's more or less the idea. Next, we start looping through and calling the adds in. It's just a matter of finding the list, right? Adding an edge, it will involve asking where to, or where from, and where to. Those from users, source vertex is loaded up, and same thing with destination. Dest vertex, helps me remember to call their variables. All right, so from this point, we can call an add, bind, find the index based on source vertex, just like we did with the matrix. And then we call that corresponding index, whatever I call the add method. Add. Pass along the destination and wait, which we need to add in there for. And so wait. How much to get there? Weak pointer, exactly what I wanted. Didn't want the weight at all. And we've added the edge. So it's just a matter of putting a loop somewhere, preferably putting that into main. Manage the loop. All right, since we're not strictly a programming class, the way you slice and dice your objects, encapsulation, proper typing, it's better if you have that laid out better, but as long as the algorithm's right, the annotation's right, and it's the right data structure, right? You're doing linked list, not an array where it should be, and so forth. Then we're on the right track. Be sufficient enough for when you turn it in as a lab program and or test question. All right, let's see. How we're doing. How did things go with our tree program? Let's check on that. Where are we? '59. So we have about a dozen people thereabouts. Can I share the code? Sure. Let's bring it back up into this space. I'm here to make sure that I didn't break anything. It seems to be working there. All right. Let's see if I'm logged in. Seems I'm logged in. And there that is. Again, it's not the full solution. It's just some of the key components. Use another dozen or two lines to get it all wrapped up. Is anyone stuck on the trees? Let's. Oh yeah, let's go ahead and spend some time with that. Let's call you tree node. Get our left and right pointers in here. And change label to name. I've got the weight. So we're good to go. Name weight. Name and weight. And just rely on the default constructor to null out those pointers. Okay. Create our binary search tree. Hey, actually, remember the semicolon that interesting. Before, so we'll need our root. I will encapsulate that one. Constructor. Just leave it empty. Setting the root to null should be good enough. Always add in if we want to or later. And void add, taking in name weight. And if the root. So this is one of the places where, depending on your compiler, you do need to be careful because some compilers, they won't actually explicitly null this out. So my logic's going to be quite broken to start. All right, lowest weight. Yeah, we'll do the lowest weight first after we get the tree built. We'll do a traversal first just to make sure the tree exists properly. Name and weight. If that's not the case, we'll just find tree node star parent. Yeah, we should call it. Yeah, parent's good enough. It's root. If the parent. Let's see. Left is less than the name. And we'll go right. Check to see. And I didn't mean to say ellipse. Parent name. All right, so if there is no right, wow. Interesting IntelliSense we have here. So if the right is null, just go ahead and attach. New node there. Tree node name, wait. Otherwise, go ahead and slide the parent that way. Now, part way there, one of the things we're doing is we're repeating code. It's best to avoid repeating code. Whatever we're going to do, except for a duplicate value, we're most likely going to go ahead and create a new node. All right, so depending on duplicates, how we're handling it, I suppose there's one path where we wouldn't actually create nodes, create a memory leak. So I guess we'll just leave it as this. All right, so else. Same story, different direction. Change our operator. Copy, paste. Change rights to lefts. And otherwise, we just won't do anything. We'll just do a silent rejection. Just leave it hanging on the phone, wondering why no one's talking back when I asked it to add a duplicate value. But if this is all going according to plan, print in order. Should work well. All right, so this one will be the helper method. The root is empty. Sorry, nothing to print. Otherwise, call an overload. Call an overload with the root. Oh, let's go ahead and, oh boy, get a little extra grabby one in the private section because they should have access to the root to be able to call it. So there's no point even exposing this. Let's see, if else line 44 and 51. Of course, I changed the line numbers on you. Let me put a white space there. I assume 44 and 51 were these two lines, and it totally should not be. I meant to switch that operator and it didn't switch. Now it is, thank you. Now you had the right line numbers. My line numbers changed between you typing and me reading your question. Yeah, I think I deleted it and then replaced it with the exact same value that I deleted, thus not changing anything. Okay. All right, so our helper checks. If our root's null, we will not do anything. We'll just return back. Otherwise, in order traversal, on the left, see out the roots name. Whatever. We can do the weight as well, and we'll do the weight as well. Might as well, whatever. Some white space, root weight. That way we can see everything. Extra white space. I guess a comma will work in there. Good enough. And then the other side. All right, so we should have enough here to test a working tree, and then we can build things up. Okay, string name, float, weight, and while name not equal -1. Go ahead and prompt name and weight from the user. And then add those to the tree. And then we'll dump out, I call it BST. Pop things out as we go to make sure things are growing appropriately. Add in our name and weight. And we'll print in order. Okay. So Mike 200. So we have Mike and 200 as our output. Looks like I can use a new line. So let's fix the new line. That new line. Here. And do that again. All right, Mike 200. Now we got Carla 100. All right, so Carla's printing out the right order. So it was on the left side. So let's test the right side. Zach 150. All right, so our tree's doing well so far. Alphabetical order. So let's put one in the middle there. We can do Tina Oh, looks like we have a little bit of bug there somewhere. Tina has failed to find her way into the tree. So either the traversal's failing or the add's failing. Let's see. Left, left, parent left. All right, so let's rely on the debugger. We'll try Tina again and see what kind of state we have. Let's get my watch window. Auto should be good. Pin that. So right now, we are at mic 200. It says we're going to the right. All right, there's already someone on the right. So we're going to go ahead and move that way. So we moved over the Zach. Oh, I don't have a loop. That would be a problem. Yeah, exactly. You got there just before I did. Good idea to have a loop. While parent is not equal to null. And let's use the right language, not equal to 0. All right, give her a breakpoint and let's get rolling here. So eventually we'll run off the end or we will attach and then run off the end. So testing again. I don't care about the numbers really. Mike, Carla, finger smash, and my loop is broken. His parent is not shifting, so let's get out of the loop. Break out of our loop. Break out of our loop, and our duplicate case just breaks out of the loop. All right. Mike, 200, Tina, 150, Carla, 25, Zach floating in there at some number. I haven't lost anybody yet, so that's good. Sandra, 11. All right. World's back in order. Except for the fact that I've got the extra input and then the weight, -1. Minor details. So the weight, finding the smallest weight. Smallest weight. This will be the helper method. The root is null. All right. Different message. There is no smallest. There is no data. Otherwise, call the one that's going to do the work with the root of our tree and move along from there. Tree nodes, okay. Root. All right, so our base case for recursion, like before, if we run off, we want to stop. Otherwise, we want to find the smallest. So our float smallest is equal to the node that we're at the moment. Then we have left smallest is call this function on the left. In fact, we want to return data. All right, so there's two ways. We'll just do the weight itself to start. That's the float. So print the smallest, or find the smallest on the left. All right, so the left smallest is lower than smallest. Let's go ahead and update the smallest to be equal to that. And then we'll get the right smallest. Same story, but on the right side. And then do a similar test here. Now, since we're trying to do mathematical comparisons, we'll do some different small s. Probably spelling that word wrong, but anyways. 2, 1, 2, 1, 2, 1, 2, 1. A big number. How many enough digits there? I think it should be range. So at this point, it will just spit out the smallest value. If things are going according to plan, copy paste error, let's fix that. And we will see out. Our data. Okay, let's move this back online where it's easier to automate our testing. Mike, 200, Tina, 150, Zach, 76, Carla, 125, and then our -1. And let's see how that goes. Of course, I didn't actually call it, so that's not going to go extremely well. So let's get the smallest, what I call a function, print smallest weight. It's possible to write temp weight less than temp left weight. Yeah, that's definitely something we can do, and we'll do some tweaking as we go. I should actually add some context here. That'll also be helpful. All right, so let's get my output here bigger. So we added Mike. They were the smallest. We added Tina. They became the smallest. Added Zach. Tina was still the smallest. Carla came along. And -1's breaking my code. It actually got into the tree. But otherwise, the smallest weight was working. So let's adjust. All right, so there's two ways. Right, two ways of doing base case analysis. Since we're within our private method or function, right, we know we're only ever going to be calling this function if the root is non-null. So we can take away this approach. And the other thing we can do, instead of returning back a weight, we can return back a node. And returning back a node means we can then print all of the data. All right, so our smallest node is that root until we find someone smaller. And let's see, we'll do tree node, tree node. Are we smaller? So we'll ask left side like before, smaller. And then we can compare, right? Are we smaller? Their weight less than the weight of the node that we're at. Smallest is equal, are we smaller? And then we do the same thing again. Reuse the same variable. Find someone smaller on the right-hand side. Right. Here we have potential problems because we know that these could be null, right? So if the root, remember I changed my base case test, so we have to control the entering into our function. And right now I'm not controlling that, so we need to be careful here. How we do this, we need to get a check in there. And then we do the same test again with a new pointer and return back that node. So let's make that test here. If there is some work to do, we'll go look for that work. And then we'll do the same thing on the other side. And see if there's additional work to be done. And we tabs. Right, so because we changed our base case to be a precondition call, so that we're not returning back nulls, right? Just nulls. Nulls are forever a problem. So you have to be very, very careful to make sure you're accounting for it. So assuming I didn't add any bugs there, smallest, this change our code here to actually get the node. Tree node star small equals that. And now we can go ahead and print out smallest with their name and weight. Small name, white space, and their weight. Can't I resize my window? There we go. Ah, because it was resizing that. Gotcha. All right, and test our code again, see what we broke. Yes, need a star there. Try that again. Conversion errors. Yes, I like to repeat my stars because you just don't do that in C#. Where else did I forget a star? Nope, you're definitely not in scope because I changed my names. All right, so now prints out. Mike is 200, so just print out 200. Tina, Carla, and we're out of time. Yep. Well, you can compare n to a null. And if the n is 0, then it would be true because null is just 0. Right, seems like I have a little bit of bug here somewhere because -1 is stopped. Input error, this could be the online pattern, who knows? Yeah, you can compare n to null, and if it's negative, right, because the value null is just 0. It's not a reference type in C++, it's just 0. So if your number's negative, negative is less than 0. If it's positive, positive is greater than 0, and 0 is 0. Okay. Any last minute questions? Right, so I will be releasing the test. You can start it now. You can start it later tonight. You can start it anytime tomorrow. As long as you start it before 11 p.m. tomorrow Pacific, you're good to go because that means you'll have it done by midnight. It's still the 65-minute window as we had with the last test. So I will be here in the chat window. In case you have questions, while taking the test, if you're taking the test now, if you're taking it later, right, then you won't have real time. No, you can use your book. It's fine. Okay, let me go find the test. Trees. Okay. All right, so the test is now available. The results will be fully restricted until Wednesday. Go ahead and start. I will also make time announcements in case you're taking it now. Otherwise, you'll need to watch the clock on your own. Going on mute. We'll see you next week, and I'll have an announcement of that in Canvas. So check that out.